Welcome back to part 3 of a 5-part training on how to use Apache Spark with Redis. What we've looked at in the first 2 sections of this training so far are the kind of Spark basics. What's Spark 101 look like? How do you access the Spark session? How do you import data to work with? How do you transform and mutate that? How do you mutate data using Spark SQL Spark SQL functions? And then also how to save that back to Redis. One of the big reasons for using Redis with Spark is that you're now able to store memory footprint of Spark computations outside of the Spark process. So instead of having to worry about going back to disk or going back, some other kind of disk I/O, through say like an EBS volume, or going back to maybe an HDFS. In this case, there's nothing to kind of load off of disk. You're just basically reading it directly out of a different memory resource. So it's actually really, really fast. And we're going to keep on looking at how to continue using Spark and Redis today. So part 3 is how to do kind of the feature engineering process. So we've looked at how, like in part 2, we've looked at how to explore data and understand kind of the underlying patterns of data, figure out how to further enhance data when you can't really answer all the questions that you want to answer with that data set. So we looked at basically extracting out categories, which were basically in the listed in column of the Netflix data set. And then how do we basically explode and split that data to create a reference map from a show ID to an underlying category. Then we use that to be able to start this next section. So given that all of that was us working with the mindset of a human user, we're now looking at how to change our underlying data to be best represented for a machine. A machine doesn't think like us. They think in orders of zeros and ones and other kind of numeric data. So all we're going to be doing with our feature engineering is going through the process of indexing, encoding, vectorization, and then from there, how do we attack a problem with unsupervised learning? So how does clustering come into play when kind of further understanding how to do your feature engineering? And then we're going to end off with some other cool stuff. So let's get started. We've been following along with parts 1 and 2, and also gone through the intro to how to work with the Zeppelin, how to get the Docker container and everything else up and running. You'll know now, basically load a notebook, attach and bind both the Markdown and the Spark interpreter. So you can basically read like the inline documentation. And then all you do is basically run paragraphs. So you can either run all, or you can run everything paragraph by paragraph by paragraph by paragraph in the notebook to kind of really understand how transformations are occurring. And also maybe, play with that as well. Change it, see what works for you. If you have a reason to go further and kind of explore, more, this is yours now. You can do what you want with it. I've just kind of laid a groundwork as a kind of series of 5 videos to get you to streaming. So without further ado, here we go into feature engineering and transformation. So we've talked a little bit about our machine learning problem statement, and I think that this is something that's really important for all machine learning projects is what is it that we want to achieve by going through the effort of creating a model? What is it that we want a machine to do on our behalf? In this case, given that this is more of a pet project for for teaching, we're going through the process of being able to mark something as kid safe or not kid safe. This is something that is, think about potential issues, say using the Netflix, use case. Say things are, encoded incorrectly, and we have, that maybe an incorrect, rating or category applied to, again, an Eli Roth movie. Right now, we have to take the system's word that the categories and ratings are correct. But if you were to maybe extend this a little bit further, you could also be parsing the descriptions, taking a look at the directors, taking a look at who are the actors that play in these movies. And you might be able to find out a way of also ensuring something is kid safe by also potentially maybe removing the rating as well. So is there more that you can do with that? And I can talk a little bit more about how to extend this project to go further. How do you explore further along like what's available in like the Spark ML lib? But for this use case, we're looking at trusting what the data says. We're hopeful that it's all correct. I've scanned through a lot of it. There's only 6,000 movies. Everything seems to be correct. But this would be part of that kind of cleaning process where you'd want to inspect the data and ensure that it's actually valid. So back to the machine learning problem. We're making sure that we can teach a system that has no idea what is a category or a rating, what is TVMA, what is PG-13. We're going to teach it how to actually think in terms of just, what does it see for patterns? Machines are good at pattern recognition. Humans are also good at pattern recognition, but we'll find out that it's actually really easy to basically teach a small kind of subset of how to actually, how to teach a machine learning model how to understand ratings. So let's go without further ado. We're going to go further. So one of the things that we are going to be talking about over here is basically the process of converting like string data, character arrays, into something that we can start to work with from a machine learning model point of view. So this is basically the process of taking a look at indexing. So if we have categories and we have a finite number of categories, say we have 15, we're going to probably have an ordinal value, which is a numeric code, which represents that individual category. So you might have 0 to, say, 14, if you're on a 0 index basis, or 1 to 15. And from there, that's basically just a way of kind of encoding your data for this kind of smaller footprint. So we don't want to actually pass in these strings and have to parse the strings and do a lot of work with it. Let's just represent that with numbers. So that's actually all we're doing over here. So if we take a look at this indexer, we're pulling in the Spark ML feature string indexer. So we're saying if we have a value that we haven't seen before, let's keep it. There's basically something called like underscore unknown. So it allows you to continue to use the same kind of fitted indexer moving forward, but also you're not going to basically break a system. So you can ensure backwards compatibility is still a thing. And you can take a look at all of this stuff online as well. The Spark docs will go into a lot more detail about all the methods and all the kind of the customization options for all of these different methods. But we're taking now a look at category. So category, as we said before, was a string label. That category now that we exploded out during part 2 of this workshop, all we want to do is basically take that and index it. So over here, we have our string indexer. This one's for rating. Same exact process. Take data. So before we looked at with column. So all we're doing with the string indexer is saying, take this column, rating. Now we're going to basically use our encoder. And the encoder is going to basically take a look at all of the data within the data frame. And it's going to then create a distinct value for the rating, alphabetize it, and then it's going to basically apply like a 0 to n on that. So that's like that's what it's doing behind the scenes, is basically just allowing you to have an index. And you can do this however you want to as well. So I kind of show a way of kind of making this a bit of a quicker process as well. And then we're also kind of going through looking at how do we handle invalid and what are some of these other options. But if we say we take a look right now at our fitted category indexer. So we have the category indexer over here. All we've done is basically say, here's the input column, and I want to now create a new output column. So it's a transformation like we've seen before with our functional transformations. So all we're going to do is basically fit the category indexer with a subset of our data for category. So we're saying, okay, well, instead of feeding it all the data, let's just give it actually the distinct values to help with this whole entire process. Same thing with the rating indexer. We're saying just go ahead and fit with what we have as distinct values at this point in time. If this changes in the future, then the string indexer itself can basically handle the invalid types as well. So it also helps you to debug what's going on. So say you have a null. All right, so content with index categories. So there's this notion basically, if you've used like scikit-learn before, you basically have estimators and you have transformers. So the whole entire process of being able to say I have basically an input column and an output column. If I want to transform, that process is just called a transformer. We're going to look at that in a little bit more detail as well. But if we call fit's basically the process of estimation. So when you're using basically like an indexer, it's not necessarily kind of a full-fledged machine learning model, but it's going to follow the same exact nomenclature. So there's always potentially a transform and a fit. And then from there, you can kind of continue to expect how everything's going to work. So everything's following a very kind of strict interface, which allows you to understand how to apply the same knowledge that you've gained in the past to new MLlib methods in the future. So say there's new algorithms that come out, you can apply a lot of the same stuff directly to that. So we're going to look at that as well in part 4 when we take a look at logistic regression and linear regression, using all of the same concepts that we're going through right now. So we have fitted and transformed the content with index categories and the contents with index ratings and categories. So given that we talk about like this immutability, so our val is basically an immutable piece of memory behind the scenes. Sorry with that dictionary. I'm using a trackpad, and sometimes it will highlight. So content with index and categories. So we're going to transform content with categories. Then we're going to take this content with index categories, and when we transform our rating, we're going to basically apply the prior transformation to that. This is a kind of loose way of doing this. We're going to take a look at the transformation pipeline later. Because say somebody goes through and edits the code later, and these things are now out of order, you might actually lose part of your data, which is kind of, it's brittle, and there's much better ways of doing this using pipelines. But, all right, so that's pretty much the process of string indexing. One of the things I wanted to show is that also you have the ability to basically reverse from your encoded index all the way back to the original string value as well. So it's actually safe to remove from your data the actual underlying category or the underlying rating. So you can actually reduce the size of the data that you have to store in memory. And then if you ever need that data back again, all you have to do is basically thaw it back out again. So if you think about like dehydration and hydration of data, in this case, you're encoding it down to the smallest possible binary footprint. And then you can actually explode that stuff back out again, which is really nice. So this is basically that whole entire process right over here. And then when we run this actual paragraph, we'll actually see all of this stuff happen. And it's going to be in like the standard out. So let's go ahead and just run this. So running. You'll see a lot of updates on the running. This is basically a bunch of stages and tasks that are executing behind the scenes in the Spark context. All right, so that's all there. Wonderful. We see that we are actually taking a look at the data directly from Redis versus anything that's loaded into Spark memory, which is also just kind of proving that point that, by extracting out where you're keeping data, you also have the ability to easily update. So it's not just that we want to use Redis with Spark, but we want to be able to effectively continue to use Spark while potentially having another process, say it's Airflow, Python, something else that's actually not Spark, that might be updating this data. So it could also be Spark updating the data like we've looked at it before. This also opens up a lot of additional possibilities for how you can kind of interop with all of these different technologies in the future as well. But let's go down. So we take a look over here and we see that we have basically our category index and we have a rating index. So basically the category is reality TV, rating is TVPG, we have these indices. So one of the things we're going to take a look at in a second is an interesting factoid about the way that machine learning algorithms perceive basically ranking data. So if something is smaller than something else, it's going to rank that and say that something that has a larger value is more important. That's actually not what we want here. And we're going to take a look at that in just a second. We'll just kind of continue to scroll through all of this. This is literally just showing us like what the underlying mapping is from string values to our ordinal values. And then from there as well, we take a look at the underlying schema. Take a look at basically just all of the output, which is great. So original to restored, going back over here as well. So I said we were going to take a look at all of this stuff. So rating index converter transforms our converted data. We see that our converted data has dropped the original category and the rating. So once we actually go and we transform it and we restore the converted data, we can now select the category and the category index. We can select the rating and the rating index. And that's what we have down below. Let me scroll back up. So that's from over here as well. It's basically like our final set that's been joined back together again. But as we know, basically keeping a long, a float, and a float is much cheaper than keeping a long, a float, and a string. So all we're doing is basically reducing that because binary encoding on numeric data is much faster and you can encrypt it you can basically compress it much better. All right. That's our first look at feature engineering. It's a very simple use case. I've got some background material as well. If anybody wants to go and read up further about what is it that we're going to be doing next. But what we're doing next, just to really glance over all of this, is that we're taking a look at Kmeans clustering. So I like to think about Kmeans clustering with the traditional apples, bananas, and basically a bowl of fruit. So if you have a bowl of fruit and you scan it as a human, and you're not colorblind, even if you're colorblind, you'll still see different shades of color, but you'll understand very quickly size. What is the size of the fruit? Is it an apple? Is it a banana? Is it a peach? Is it a pear? A lot of that fruit has, basically, if you were to drop it into buckets by size, you have additional kind of size. So say now you have cherries, you have dates. I don't know if a date is a fruit, maybe it's a vegetable. I don't know. But for the dates and everything else as well, you'd basically put that into different sizes. So it's same thing with any kind of thing that you can think about as like a logical hierarchy of scale. Everyone's seen that picture where you basically have, from chimpanzee all the way to human, and how we've kind of moved to having like an upright back. Now we're moving back down with smartphones because we're always staring down. But in general, like what we've done well as humans in general is be able to kind of really understand patterns quickly. And that's helped us also, like if you think about the sociology of like fight or flight. We're able to size up, potential problems very quickly and decide if we should basically encounter a problem or literally really quickly go away from them. But back to the whole entire bananas problem. So if you were to actually create a Kmeans clustering, say is Kmeans clustering problem statement. It's like, I want to efficiently be able to sort fruit, but I'm a machine and I don't know what fruit looks like and I don't know what fruit is. So how can we actually understand how to teach a system how to identify that fruit and also cluster it? So you could say, okay, well, on the first pass, we're going to cluster by size. So with Kmeans, basically K stands for, it's an arbitrary number of individual cluster centers. So if we say, okay, we have 2 cluster centers, well, bananas might be in its own cluster, while peaches, pears, and apples are in another cluster, all based on size. Because the distance from the cluster point is closer to the size of a banana, or to the centroid in a cluster is closer now to apples, to peaches, or to pears. So you think about that as a kind of way of understanding mental model. That's one way that I like to think about it. Then you go into basically a distance problem. So Euclidean distance, we think about geometry. If you have an x and a y parameter in a 2D grid, now you have points that are in a 2D space. So all you're doing with the clustering is trying to efficiently partition an x and a y coordinate amongst centroids. And we'll look at that in just a little bit as well, with how it actually relates to our categories and ratings problem. We're also then going to take a look at one-hot encoding. So one-hot encoding is the process of being able to ensure that the way that we actually mark our data or encode it from an index to an encoded index is something that's not going to basically throw off a machine learning model or machine learning algorithm to incorrectly actually rank that data. And we're going to see that just now, which is actually kind of fun because there's a really quick way of testing that. We're going to trick our system into really not understanding anything, and then we're going to encode it to make it a little bit smarter, and then we're going to continue to add more smarts to our system by basically layering in a level or just a layer of human intelligence. We'll see that in just a sec. Go through this stuff later, but it basically shows the way that all of this stuff works. You're creating basically a matrix of these encodings, and then computers are good with matrices. All right, so we're going to take a look now at the pipelines. I said before that our ability to basically not screw things up as humans is hard. So if we want to be able to effectively create a synchronous process of transformations across our data and reliably be able to continue to rely on future versions of the same source code, pipelines basically solve that problem. Also, I said before that we're going to take a look at one-hot encoding versus not one-hot encoding and see how that affects rank. So right here, I already see that I've basically commented out our one-hot encoding. So all we're going to take a look at now is a process of basically creating like a vector. So in vector math, we basically have a vectorized array of data. So if you think about like a matrix, we have individual vectors of our underlying data. And in this case, we can now tell the computer in a more efficient manner how we want it to work with our data. So right here, we're creating the vector that has our category index and our rating index. And then we're going to basically output that as our underlying features. So this is the feature engineering part, where we're now making things better for a machine versus for a human, because I'm not going to understand this. And we'll take a look at what that actually looks like as well. It's going to be basically a sparse array. All right, so transformation pipelines. This is also from SparkML library, the pipeline. So our pipeline has a bunch of stages. A stages is just an array of transformations on an input data frame. So right now we've removed our encoding, and now we've changed to basically the vector assembler that's only using the indexed values. So then we indexed above as well. So like we said, there's transformations and there's estimators. So right now with our pipeline, given that you want to be able to potentially serialize and deserialize something that you need to rely on, like a pipeline, you can fit a pipeline. You can also save it for later, which we're going to look at. So if we take our fitted pipeline, so transformation pipeline fit, content with index, ratings, and categories. We've seen that from above. That was basically the end result of first taking a look at indexing our categories and adding the index, and then taking a look at our ratings, and then just combining it all together. So it's basically 2 steps of transformation, both using index to string. String to index, I apologize. All right, so over here, we have fitted pipeline, and we're going to now transform our fitted pipeline with our same data as well. Given it's not, we don't need to like hold out a test set or a train set, which we'll look at later, and that's also part of like the machine learning process. In this case, you can use 100% of our set to basically fit into transform as well. Doesn't really matter. Great, so that's basically pipeline. From there, we're going to use a very simple Kmeans model. So we say, okay, new Kmeans. This is coming from SparkML, and we have clustering techniques for Kmeans. Kmeans is under the umbrella of unsupervised learning because there's no explicit label. And a label basically dictates to the machine, it says, I want you to be able to estimate really well for this outcome. Here's a bunch of information, but I'm giving you a hint so you can optimize through iteration to be able to predict and estimate with high levels of accuracy if things are done well. Something that a human might not be able to actually write, through a series of rules or decision trees that we hand tune. So you'll actually speed up the process of getting things right more often than not. And we're not going to go into a lot of bias and other things like that during this whole entire presentation. But there are good ways and bad ways to do certain things. And a lot of times the machine learning model is like a kid learning. And if you teach it the wrong thing, it will just basically say, cool, that's great. I'm going to keep on following your lead. So if you teach it the wrong way, either basically through a biased data set, then, as people have heard in the news as well, there's a lot of problems with biasy, whether it's in, being able to auto scan for potential hires for a company or even for credit scores. So just something to think about when you're approaching a new machine learning model is how do you reduce bias in your data set? And we'll take a look later on at basically cross-train validation and also some kind of theory on how to actually bucket efficiently your training data so that you are not kind of biased more towards one thing versus another. All right, so going back to the actual problem again. So we said before we want to basically create a Kmeans cluster. The Kmeans cluster is now going to take our data, which is literally just our features. So we have our category index and our rating index. We haven't told the system in this case what we want it to do. We just want to see how things actually line up. And you'll see really quickly that if we were to try and say, okay, well, let's just see how categories and indexes, or how does a category and a rating actually show up in 4 basically cluster points. Given that we don't have a lot of data, you'll actually kind of see there's an underlying pattern that's kind of close to already figuring out kid safe or not kid safe. But in the first pass where we're not using one-hot encoding, because of the way that the indices are actually generated, we'd actually have a lot of overlap between TVMA and children's content. All right, so over here also, so Kmeans, we're setting 4 centroids, and it's going to basically randomly apply the 4 centroids to the underlying data, and then it's going to iterate through, and there's more information above in the doc on Kmeans clustering. We're also setting a seed. So if you think about seeding something, if you have a random generator, or in this case you have a random seed, then every time you go through the process of creating this model over and over again, you can actually have a deterministic result. A deterministic result means that every time you run the same data over the same model, you'll have the same outcome. And you really want this when you're actually making, when you're taking machine learning models to production, is the ability to rely on what you've actually trained. And so seeding is a really great way of doing that, even if in this case it's unsupervised. All right, so Kmeans fit transform data. We've seen the fitting and the transformation before. That creates our model. So models have to be fit. And models are now fit on the data that's been basically fed through our pipeline. And then our predictions is basically us calling transform. So instead of us transforming a pipeline by sending a data frame through a series of mutations, in this case, we're taking the underlying features, and now all we're doing is basically transforming that to create a prediction. In this case, the prediction is which cluster will this data land in. From there, I'm not going to go into cluster evaluation. There's some kind of other information here as well. You can also take a look at the Spark docs as well. But the evaluator will literally just tell you the underlying the underlying centroid data, where those ended up, and then the underlying features that are basically bound to that centroid. And that's more for a computer than it is for us. So we're actually going to use Spark SQL to actually look at the predictions. So let's go run this first. And as I had said before as well, we're not one-hot encoding, so we're going to see the ranking problem right now. So we're going to go over here. We're going to run. We're counting as total category and rating prediction from predictions, and then we're going to group this by category and rating and prediction. So we just literally want to see how things fall into which kind of category. So right off the bat, you see not rated. And say TV action adventure might be kid safe, but because it's not rated, it could also be X rated. We don't know. It could be very unsafe for children. From there, we also have, we have a kind of different distribution of things, but the not rated in the R makes me kind of sad. But also the computer is not super smart because at this point, it's literally just trying to rank data. So because we're actually telling it to just use ranking, things don't look good. Great. So let's take a second pass over that. We want to fix the ranking issue. So I'm going to change, so just comment this guy out. I'm going to go back over to the initial vector assembler. And the vector assembler takes the output of our one-hot encoding estimator. We're going to add back the transformation to create the encoder. And now all we're going to do is basically refit everything. So now we're running off of a brand new pipeline, which is taking into account our underlying vector, which is basically the encoded vector. And as we saw up above as well, when I was talking about one-hot encoding, we have basically our ordinal index to the underlying vector. And the vector is going to take, it's basically zeros and ones for all available categories versus it being something that's in rank. So instead, it's now a sparse vector of where things actually land, which is a lot easier to be able to look at because it's zeros and ones versus anything that's ranked. All right, so we ran this again. You take a look at the predictions. If you're a computer, this will be very interesting for you. Otherwise, we're going to take a look at what is really kind of easier for humans to understand. So over here, we see now that, this is all kind of a random distribution anyways, but because I haven't done any kind of sorting. But if we take a look now at our the ratings, we've got R, and R is all now bound to category 3, or centroid 3. We have kid safe stuff for the most part in category 2 or centroid 2. If we think about the prediction as an overarching category, and then we've got TV14, and then we'll see that prediction 0 is kind of a, it's anyone's game at this point. So TVMA, not rated TVG, we can't really trust it. But we tried our best, and we saw that, you can actually upgrade and enhance things just by actually changing the ranking problem for some stuff. Over here, we take a look at just another way of looking at all of this underlying data by taking a look at the average prediction across an individual rating. And so you'll see in certain cases that, now we're basically zeros, twos, or ones across the board, which is great. So not a big deal. We said we wanted 4 centroids. Now we have 0 to 3, so we have 4 centroids. And now, in general, the average prediction is at least within a specific bucket. But we also know from the left-hand screen that over here is problematic. So I updated this to basically say, it's like, given the PG movies and NC-17, because I had seen that, that show up in the same cluster. In this case, now right above, we're also taking a look at how TVMA, not rated, and TVG are showing up, which is kind of scary. Which is also, it's scary, but it's also something that we know about because, the computer, in this case, the machine learning model, has no idea what we want from it. We're trying to basically say, solve this problem. I'm not going to tell you how to do it. And if you tell anybody to solve a problem without actually giving them a hint at what they should be doing, they're going to try their best, but they're not going to actually do what you want them to do. They might, but in this case, we're going to basically teach our system how to think better. So how do we do that? So what we're going to do now, in the same way that we said, okay, well, categories are important to solving the problem of kid safe, we're now going to give a hint. So if you think about the process of going from unsupervised, which doesn't have a label, to the process of supervised, where we're saying, well, we've given the machine learning model a training set that has a known value that we want it to basically create predictions for. So in this case, we're now giving it an additional field for its rating. So we'll see over here, we have basically our ratings and we have our rating index. And so if we just take a look at our indices that we have from our original string to index, then we can say, okay, well, this is safe for kids or this is safe for most. This unknown over here is in the case of nulls. We've actually removed the nulls from this whole entire equation, but it's possible, as say in the case of other things other than ratings where we have a non-finite set of, say, labels, then in that case, the machine learning model will all basically dump that into its own underlying ordinal, so that everything that's unknown can be taken a look at, and you can kind of introspect that later. So if you want to go back and fix the problem of the unknowns, you're not necessarily breaking the current machine learning model, but you're allowing it to basically be safe for upgrading later. So you can use it for debugging models, which is a really important thing as well, because a lot of times a model feels more like a black box. But if you can basically introspect what's actually feeding the model and feeding the machine's understanding of a problem, then it's a lot easier to make it think better. So all we're trying to do is basically teach it to think and recognize patterns. All right, so we have safe for kids, safe for most, and then everything else is going to basically drop into like a unsafe category. So we have this notion we were talking about before of like using like our with columns. So we have this with rating classification. We're taking a data frame as input, and now we're actually returning a data frame. So this is kind of a simplified version of what we will see like in transform pipelines when we create our own down the line. But all we're doing here is basically saying, well, our data frame has a column. We're going to add a column called rating class. When the rating index is in the collection of safe for kids, we're going to basically say it's 0. When it's the rating index isn't safe for most, we're going to give it a value of 1. Otherwise, we're going to give it a value of 2. So a really kind of easy way of making something that's kind of human friendly by using the when clauses in Spark SQL or even in SQL in general. So now we have this content with ratings classification. And all we've taken is that initial set where we transformed before. So content with index, ratings, and categories, transform with ratings classification. And then we can print our schema, and now we can basically create a new view of our underlying data called rating classification. So let's go and run this. So we've run this. We see now that we have a show ID, a category, a rating, category index, rating index, and rating class. So rating class is a double, and it already has its own index. So we don't actually have to go back and do anything different here. We don't have to use like a string to index because we already have a value that's indexed. So now we can actually go ahead and just add our one-hot encoding to this as well. But first, let's take a look at our classifications, because we have that ability with Spark SQL, and we also have the ability to easily visualize this, taking a look at that through Zeppelin. So we'll see that we keep on basically, we're hitting Redis for all of this. So anything could change in the background, which is another reason why like having the unknown support is really good, because in typical kind of production scenarios, stuff will mutate without you knowing it, and being able to adapt to change in a way that you see fit means that you don't have problems like in production or outages, which is good as well when that would be problematic. So selection from the rating classification. So we'll see like reality TV, TVPG, category index 2, rating index 0, rating class 1. Awesome. And this basically, if you go through it, you'll see that the rating class will never deviate from what we've told it to do. So we've actually labeled it now with basically 3 different classes that we want to train our model for. And in basically the case of Kmeans, we can also now use this additional information to actually ensure that there's no bad content across our different centroids. So it's kind of like a mixture of supervised learning in an unsupervised model, which is kind of an interesting way of looking at things too, because what we're doing is basically just creating a score about how close to a centroid is a chunk of content, in this case a movie or a TV show. All right, so we've seen this stuff before: pipeline, one-hot encoder. We have a vector assembler. We've got our Kmeans, and we've got the cluster evaluator. So I've put this note in here, which is the same thing that I have above. I'm just going to edit this, and then I can update for everybody else later. There's that Apple dictionary, which shows up so often with the trackpad. All right, so this one, we're now saying, okay, well, before when we did our transformations, we had a, kind of a series of, we had our pipeline. So we're doing the pipeline over here as well. And all we're doing is basically changing the input columns. So we're adding an additional input to basically generate our features. And that's our rating class. So we're still creating a rating vector. And then we're assembling those vectors back into our features. So now we have 3 features to be able to train our model with. In this case, again, it's unsupervised. So it's going to be sliced and partitioned across our centroids. So let me have it up with water. All right, so transformation pipeline, we've seen this before. I just wanted to change this so that we know that it's not affecting, if we were to do reuse, and we didn't run this for some reason, then we could actually basically spoil this whole pipeline by using something from a different paragraph above, because it's all using the same Spark memory. So in this case, we've just redefined everything so that it makes more sense in the second pass through. All right, so running, great. So we've got our vector assembler, we've created our pipeline. I'll remove this as well. No dictionary that time, that was wonderful. So our fitted pipeline, same thing we've seen before. I set the centroids to 6. We can also put it back to 4. Doesn't really affect anything. But when you're testing, in this case, it's kind of easy to keep on rerunning and experiment. We're going to look at grid params in a little bit, which basically tells Spark to go try a bunch of different things and tell me what worked the best, which is really good for supervised learning where you're trying to predict the best underlying outcome. In the case of unsupervised, right now we're just kind of playing around, and I consider this, it's a little bit like the exploratory data analysis, but now it's for exploratory feature engineering. So, how do things land when we've now given this an additional feature in the case of category classification. All right, so we've now done predictions new over here. So predictions new, doing basically the same stuff with the Spark SQL so that we can take a look at the human-friendly version of what our predictions looked like. In this case, we're also taking our prediction and we're basically calling that cluster. So we say average prediction is cluster. So, rating class 2, cluster is 3, rating class 2, cluster 3, cluster 2, 0, etc. So you can scan through that as much as you want. We could basically scroll forever. We don't really want to do that. But what we've done is basically apply additional kind of domain knowledge to our actual modeling process. So this is actually something that I find super useful when you're attacking a new problem, is to say, okay, well, what do we actually know about this? So is there something that we can actually use as a hint to be able to make a better model versus trying, basically trial by fire to figure out what works best? So you can actually save time by applying domain knowledge in the case where it's a problem that can actually be solved by domain knowledge as well. And so that's pretty much kind of it for this whole entire section. It's a very kind of quick walkthrough of the whole process of creating features from underlying data from a data frame to help steer a machine learning model in the right direction. And this was all unsupervised, which is great if you have no labels. But we've also seen that if you add a label to unsupervised models, you can actually get better results when you're clustering without a explicit label. All right, so we can take a look at what we've learned. You guys can read through that on your own as well. You can ask as many questions as you want during the Q&A section, or you can literally just go through and read all the documentation as well. But in summary, what we've learned is basically how to add a class, which is our rating class, how to use the string indexer and one-hot encoder, and why one-hot encoder actually affects rank through the example that we saw above, where by not actually using one-hot encoding, we had a lot of unsafe content show up in our underlying clusters. So what we're going to do in the next step, and in the next actual training, which is going to be part 4, is take a look at how do we further extend this process to make a really, really solid and sound pipeline, and how do we actually go ahead and use supervised machine learning techniques like logistic regression and linear regression. We'll also talk a lot more about what linear and regression and logistic regression are actually trying to solve for. And then from there, we're actually going to go through and in part 5, we're going to take a look at streaming. So I hope this has been useful. If anybody has any other questions, again, Q&A section, Q&A session is going to happen. Otherwise, also reach out to me on Twitter at Newfront. Thank you very much.